Right. Okay. So today we are planning to discuss a few model questions from electricity. Okay, it's a very important unit. Electricity. Uh, there's a possibility of you getting a structure essay question, and there's a possibility of you getting around 5 to 6 MCQs. And every year there will be an essay. There will be an essay, but it's not a must to do that essay. But personally, I would recommend you to do electricity because it's not very difficult. Electricity, that is like electronics. It will come with electronics. So compared to electronics, electricity is somewhat manageable. But anyways, okay. Let's quickly go through this and let's see how far of the content of that syllabus we can cover. Anyways, the first question, part A. Part A. Right. Okay. Use the definition of electromotive force of a battery E and current I. Show that power delivered by the battery is given by IE. Okay, now what is the definition for electromotive force? Answer for Roman 1. Definition for electromotive force is electromotive force. Wait a minute. Electromotive force. Electromotive force is given by energy provided per unit charge. That is the definition. Energy provided per unit charge. So energy over electric charge. That is the definition for electromotive force. Energy provided per unit charge. So if I put that into symbolic form, E equals energy over charge. I'll just say energy because if I put both E for both, it will be confusing. Over charge, we'll put Q. Then what is it, right? So energy is equal to EQ. Energy is equal to EQ. Don't get the wrong idea. E is for electromotive force, not for energy here. Then dividing either side by time. Dividing by time. So let's divide either side by time. Dividing by time. What will we get? Either side when you divide by time, you will be getting energy over time on the left side. And on the right side, you will be getting what? E over qt, E into q over t. Okay, q over time. So we all know energy over time is power, q over time is current. So you can say power is equal to E into I. And I think that's what they are asking us to derive. Yeah, IE, finished. Done. Okay. And then the equation for the power dissipated in a resistor R, P equal I squared R and P equal V squared over R with usual notations. The first suggests that P increases with R, while the second suggests that the opposite. Resolve this apparent contradiction. Oh, what is this? Read it again. The equation for the power dissipated in a resistor R, P equal I squared R and P equal V squared R with usual notations. The first suggests that P increases with R, while second suggests the opposite. Yeah. So Roman 2. You take Roman 2 people, now there are two equations. If P equals I squared R, so when you have a look at this equation, it says that when your resistance increases, power should increase, right? And the other equation is P equal V squared over R, but here they are saying when resistance increases, power reduces. Can we say that? Can we say that? We can say that only now. This is important because something you have to understand is this. What is it? Based on this, I can make a conclusion, that is power is directly proportional to resistance. Power is directly proportional to resistance when? Proportional to resistance only when who is constant? Only when current is constant. Current means I. Current is constant. If the current is not constant, you can't say that power is directly proportional to R. All right. And here, using this equation, you can define power is inversely proportional to resistance only when who is constant? Proportional to resistance only when voltage current V is constant. So you can't generally say that, because you can't barely say that P is directly proportional to R, and you can't barely say that P is inversely proportional to 1 over R. You have to mention that the other quantity there is constant. Okay, so what happens to power is actually, what is the relationship between power and R, people? We have learned when you have a circuit like this, in case when you have a circuit like this, when you have a resistor like this, and when this has E and simple R, and when this has R, okay, so if there's a current flowing through the circuit, and there will be a V across this one, yes, and if you draw a graph of power, we have learned what will happen to power. Power doesn't always increase with resistance. Power doesn't always increase with resistance. Power doesn't always decrease with resistance also. It increases and then reduces like this. And what will be this value for R? What will be this value for R? When is power maximum? When is the power dissipation maximum, people? Anyone? When is the power dissipation maximum? When this capital R becomes equal to who? When this capital R becomes equal to simple R. When capital R becomes equal to simple R. So this capital R has to be equal to simple R. Sorry. X-axis is for capital R, the external radius. When that capital R becomes equal to simple R, that is when power is maximum. And can anyone remember the equation for the maximum power, people? To get the maximum power here, maximum power, and what is going to be maximum power? Power maximum has an equation which is going to look like this. Power maximum is equal to E squared over 4R. RR E by 2R, squared of that here. R squared of E squared of 4R. That is maximum power. I think if you can explain these two, it's enough. So you can always say that the power will increase with R, or you can always say that the power will decrease with R. It depends on the magnitude of R. Based on that, you can say. If not, you can't directly say that R is going to, when R is increasing, P is increasing. When R increases, P increases. We can't directly say that. You can say that if you find a way to maintain a current constant. You can maintain current constant. For that, what you have to do is what you have to do is, you have to what was I saying? You have to connect another variable resistance here. If you have another variable resistor here, you can maintain the current constant. You put an ammeter across this, and by changing that variable resistance, you can always maintain a constant current. Okay, then yeah, then you can find it. Anyways, that's how it happens. So, okay, so that is how you resolve this contradiction. Done. And then let's move on to the next part, that is part B. I think the earlier part is part A. It is covered, that A is covered. Anyways, part B. The initial part helped us revise something under power, and now we are going to focus on resistance. I think resistance. Let's quickly get started here. The current in the starter motor of a car is 160 ampere when starting the engine. The connecting cable has a total length of 1.3 meters and consists of 8 strands of wire. 8 strands of wire. Okay. 8 strands of wire, each of diameter 1.2 millimeter. The resistivity of the metal of strands is 1.4 into 10 to the power minus 8 ohm meter. Right. So, Mariam, I just saw your message. To explain the graph, I will have to take an extra time for that. That graph, I'll have to now. In the theory class, what I did was I took different values for R, 1 ohm, 2 ohm, 3 ohm, 4 ohm, and then I actually calculated the values and showed them. The problem is you can't get an equation and get this graph. Okay, you can't get a specific equation and get this graph. I think you will have to remember this for the time being. That's all I can tell you. I can explain this, but it will take a lot of time. We have other questions to discuss, so I can't dive deep into this theory, but I'm sorry. You will have to cover from your theoretical class. For the time being, this is all I can say. This value is going to be E squared over 4R for a circuit which looks like this. For a circuit which has a battery E with internal EMF E and internal resistance R, and should have a resistor like this, variable resistor. Okay. Next one. Now moving on. Next question. There are 8 strands of wire, each of diameter 1.2 millimeter. The resistivity of the metal is 1.4 into 10 to the power minus 8 ohm meter. Looks like we will need to use pi here, but they have not asked us to use 3 for pi, so you can't use 3 for pi. Sorry. When you have 8 strands of wire, you know, when you see the wire from the side, you will have 8 strands. 1, 2, 3, 4, 5, 6, 7, 8. No? You will have 8 strands of wire like this. You must have seen these copper wires. So if they say it has 8 strands, it's going to look like this. No? It's going to look like this. It's going to look like this. 8 strands of wire. No? Get my point? Right. How are they? Now, if you have 8 strands of wire, are they in series or parallel? Are they in series or parallel, people? The 8 strands of wire. They are how are they? They are parallel, right? They are parallel. Now, if you take a wire and if you cut it, you will see these small copper wires. So they are in parallel. Yes, 8 strands in parallel. That you have to understand first. 8 strands in parallel. 8 strands in parallel. Okay. Calculate the resistance of each strand. Okay, calculate the resistance of each strand. For that, what we can do is we can use this equation. What is the equation for resistance? Roman 1, you can go with R equals rho L over A. R equals rho L over A. Sorry. R equals rho L over A. So resistance R equals rho. Rho will be what? Rho is the resistivity, 1.4 into 10 to the power minus 8 into length, into length. Into length minus 8 into length is 1.3 meters, no? 1.3 over 1.3. Area, for area you have to put pi, 22 over 7 into diameter is 1.2 millimeters. See, diameter is 1.2 millimeters. That means radius I can take it as 0.6 millimeters. Now I have to be very careful here. 22 by 7 into my goodness, this is going to be 0.6 into 10 to the power minus 3 squared, no? Square. This is the correct substitution. Yeah, I thought 1.4 will get cancelled off. It is not getting cancelled off like expected. Whew, right, okay, never mind. We'll find it. R is equal to, on top now we have 1.4 over 1.3. I think we can simplify it a little bit. That 22 here will make it 11, and on top we can make it 0.7. So on top I'm going to get 7 into 13 or 7 into 1.3 into 10 to the power minus 9. If I make it 7, I have to make it 10 to the power 9. So 9.1 into 10 to the power minus 9, and at the bottom I have, oh, that 7, this 7 will go up, no? And into 7, then into 7, this 7 will go up, and at the bottom I have 11 into 0.6 squared is 0.36 into 10 to the power minus 3 squared is 10 to the power minus 6. So R is equal to 9.1 into 7, 63.7 into 10 to the power minus 3. Why? How did 10 to the power minus 3 come? 10 to the power minus 9 divided by 10 to the power minus 6, 10 to the power minus 3 divided by 11 into 0.36. That is going to be 3.96. 3.96. Anyone who got the answer? Anyone simplify this, people? No? 1.4. I hope I have substituted everything correctly. Rho L over A, no equation. Okay. Pi R square. That is the area of this thing. So R is this 0.6. Answer should be very close to 16. Okay, 1.6 into 10 to the power minus 2. Right, okay. 1.6 into 10 to the power minus 2. 1.6 into 10 to the power minus 2. I think that's a good answer. Let's go with that. 1.6 into 10 to the power minus 2. Oh, almost, because 64 divided by 4 roughly, people. You can consider this almost 64 by 4. So 1.6 into 64 into 10 to the power minus 3 rather. 1.6 into 10 to the power minus 2 ohm. Calculate the total resistance of the connecting cord. 8 strands are in parallel. 8 strands are in parallel. So what can I say? So equivalent resistance is going to be equal to what? We have to divide 1.6 into 10 to the power minus 2 by 8. 8 equal resistance in parallel means you have to divide it by 8 and get the answer. So final answer 2 into 10 to the power minus 3 ohm, because it is going to be 0.2 into 10 to the power minus 2. I will finally write it as 2 into 10 to the power minus 3 ohm. Now Roman 3. What is the power loss in the cable? What is the power loss in the cable? Alright, power loss. We know the equation for power loss is I squared R. So I square is 160 into 160 multiplied by 2 into 10 to the power minus 3. When you multiply 160 and 160, it will be 2560. 2560 into 2 is 5120. I am getting 5.12 watt. Anyone who got this answer, raise your hands. If you multiply this, 5.12 watt. No? Amna? I square into I square, because they have given the current. 60 into 16 is 256, double 0 into 2, 256. Oh, no, more, 51.6. No? 51.6. Should be 51.2 rather. 50, because 16 into 16 is 256. 25,600 into 2 is 51,200. Yeah, 51.2 watt. This is the final answer. It's just a matter of substituting values and getting the answer. Roman 4. When the starter motor is used to start the car, 800 coulomb of charge passes through a given cross section of the cable. Assume that the current is constant at 160 ampere. Calculate for how long the charge flows. That is also simple, no people. What is the equation then? We know charge is equal to current into time. Then time is equal to charge over current. So charge over current, yeah. So time is equal to 800 over 160. Now what's the time? 5 seconds. 5 seconds. Okay. Fine. So how many of this you guys got correct? Can I know the response from each one of you? 1, 2, 3, 4 parts are there. It's pretty simple than I anticipated it to be. But very straightforward. So if you remember the equations, you can get the answers really quick. No problem whatsoever. So that part is done. Then we'll move on to the next part. That is part C. Okay. Right. A whole question with the circuit diagram and all. Fine. I hope the readability is fine. Let's start. Now suppose that the starter motor is connected with a battery. Suppose that the starter motor is connected with a battery. Suppose that the starter motor is connected with the battery, EMF E, internal resistance R. The resistance box R values could be varied precisely, ideal ammeter and 2 headlamps. Now when they say ideal ammeter, remember internal resistance of that is 0, no internal resistance. So for that ideal ammeter, you can say internal resistance is 0. It will not allow current, it will not allow any internal resistance is 0. Okay, it will not allow any potential drop across it. Two headlamps rated as 12 watt and 12 volt and 72 watt as shown in figure. S1 and S2 are switches. Resistance of the starter motor is 0.25 ohm. I'll mark it here, 0.25 ohm, right. And what about the battery? Okay, okay, and the bulb, two headlamps, both have the same rating, no? 12 volt and 72 watt. The meaning of that is it needs a voltage of 12 volt across it for it to for it to function normally. Right. When both S1 and S2 are closed and R is changed to 2.75 ohm, a meter reads 8 ampere. Let's read again. When both S1 and S2 are closed and R is changed to 2.75 ohm. I think this should be R, no people? This should be R, because if they are changing it, this has to be a variable resistance. Yeah, R. Then they have given the meter reading. Good. Now let's quickly analyze it. Calculate the value of E and R. Calculate the value of E and R. Okay. So how do you do it? Roman 1 now. Let me start it this way. Roman 1. Let's put the diagram. Both S1 and S2 are closed. R is changed to 2.75 ohm and ammeter reads 8 ampere. Let's put that into the values. Let's draw a new circuit. And there's a starter motor here. Starter motor also will take it as a resistor, no? Because it has a resistance, no? And then you have this thing. You have the ammeter. I'll put the ammeter because the ammeter reading is provided, and both the switches are on. That means this circuit and this circuit, they are complete, they are working. Okay, people? So now tell me, what is the voltage required for the proper functioning of the lamps? Now they have mentioned, let's mark the information provided. They have mentioned that the ammeter is reading 8 ampere. So we can assume that the current of 8 ampere is flowing, not assume, we can consider that a current of 8 ampere is flowing through the battery and the ammeter. And battery has an EMF of E into resistance of simple R. And this one now, it is 2.75 ohm. 2.75 ohm, right? And this one is 0.25 ohm. 0.25 ohm, right? So how do we now, this bulb 12 volt and 72 watt, this is 12 volt and 72 watt, 12 volt and 72 watt. Yeah, so what can we do now? How are we going to approach this question? There, should we take the voltage across this as 12, or should we normally do it? Now you can, for the bulb, we can do this now for bulb. Okay, well, for bulb, you can apply this equation. For bulb, you can say power is equal to V squared over R. For power, you can put 72. V square is 12 into 12. Okay, for over R. So R is equal to 144 divided by 72. 144 divided by 72, and that is 2 ohm. You can find out the resistance of each bulb like that. So each bulb has an internal resistance of 2 ohm and 2 ohm. 2 ohm, yeah. Right. If the resistance is 2 ohm there, what is the final value? I mean, 8. Simple R is there. We need 2 equations to finish this, no? Interesting. Wow. We need 2 equations, and yeah. So we have to assume that there is a potential drop of 12 volt across the bulbs for the bulb to function. Do you agree with me? There must be a potential of 12 volt across the bulb for the bulb to function properly, right? So here across the battery there must be a 12 volt potential drop. So let's put it that way. For the bulbs to function properly, function properly, 12 volt potential difference must be maintained. 12 volt potential difference must be maintained. So across the battery also we have to maintain that 12 volt. Then only these two will get 12 volt and 12 volt. So for battery we know we can apply an equation. What is it? For battery we can apply an equation. For battery we can put V equals E minus IR. This is the equation for the voltage across a battery with internal resistance. V equal E minus IR. V has to be 12. E we don't know, minus current through the battery is 8 ampere. So 8 R. First equation. I have two unknowns, remember, I have two unknowns. That's the first equation. Second equation, people, now there is going to be a current through this path, that is I1. There's going to be a current here. Okay, will that work in our favor? 4 ampere. What is the current through this one then? V. There's going to be a problem here. If we take it as 12 volt, if I take this as 12 volt, then one equation okay, the other equation does not tally now, people. What's the current through it then? I don't think I can take the resistance as 2 ohm then. Can I take the resistance as 2 ohm? That is the problem now. If I take resistance as 2 ohm, this is 1 ohm. Through this the current definitely has to be, if we need 12 volt here, the total current is 4 ampere. So if 4 ampere comes here, 4 ampere goes here. So 2, then there's a problem. So power will be different, is it? Okay, we'll do it that way. Now, but will that be helpful for us? I need another equation for 12 volt. What is there? What is the current then? Okay, 12 volt now. Okay, we'll forget about this resistance for a while. We'll do this question without considering the resistance. Wait a minute. We'll forget about this 2 ohm for a while. Not focusing on that. Let's try to do it this way. Now, here on this side, we have 2.75 and 0.25. And what is the value of I1? I1, you can find I1 by applying, so what do I say? The circuit can be redrawn like this, 2.75 and 0.25. They both together will form a 3 ohm resistance of the left corner, 3 ohm. And the battery is here. And yeah, the rest is the two, what do you call that, the bulbs are here. Now 8 ampere current is flowing, but ENR are unknown. Yes, no problem. We know that the potential difference across this should be 12 volt, then only the bulb will function properly, 12 volt. Then same 12 volt must be across this 3 ohm. Why? How did I get 3 ohm? 2.75 and 0.25, they both are in series, so I can put it as 3 ohm. 3 ohm is 2.75 plus 0.25. Okay, so this, for this 3 ohm, if I apply V equal IR, V will be 12 I will be I1, we have taken the current going through that as I1 as in the previous diagram into R is 3. So I1 is equal to 4 ampere. I1 is equal to 4 ampere. There's 4 ampere current flowing. And now for this circuit, let's try to apply Kirchhoff's law, that is sigma E equals sigma IR, and let's see if we are getting another equation. Sigma E is E, only one battery is there. For sigma IR, we have to put current is 8 going through the internal resistance impeller, so that is 8R plus on the other side 8R plus here the current is I1 going through 3 ohm. So that is 3 into I1 current is 4. So I'm getting the same equation once again. No, oh god, no, it's not going to be helpful for us. We are getting the same equation once again. Try it that way, it didn't work. Come on, man. Same equation once again, that's it. Meter reading 8 ampere. Yeah, 4 ampere and 4 ampere. So if 8 ampere goes here, 4 ampere comes here, then remaining 4 goes here, 2 ampere, 2 ampere. 2 ampere means, doesn't make sense now, people. You must have given two equations and x1 and s2 are switches. Resistance of the starter mode is 0.25. Okay, we have marked that. Think that all the resistance of the wire connected, yes, both S1 and S2 are closed and R is changed 2.75, a meter reads 8 ampere. So I have first equation here. Anything else? If not, we'll take this as an unknown then. 12 unknown ke lagatta, we don't know this current means. If we take this voltage to be unknown, then how many unknowns will I have? 1, 2, we don't know E, we don't know R, and we don't know this current. 3 unknowns, so we can focus on 3 equations maybe. Okay, sorry, we'll do it this way. I think if I tried it that way, it didn't work. So it's for the proper functioning of the bulb, na people. It's for the proper, this 12 volt and everything is for the proper functioning of the bulb. So let's forget about that for the time being. Forget about that. And yeah, 8 ampere is here. I1 gets split there here, and here we'll get a current of I2. Then what will happen after that to that current I2? Then I2 flows here. Then you know what happens. These two are identical bulbs. Therefore, I2 will separate to I2 by 2 and I2 by 2. We'll take it that way. We'll take everything as unknown. I2 by 2. Okay, that's what's happening here. So these are just the rated voltage and rated power. The meaning of rated voltage and rated power means if the power and voltage are that value, then only this bulb will glow with its maximum brightness. If not, it will glow, but with not its maximum brightness. So let's do it that way. Now we have to write equations. How many equations can we write for this? Yeah, we don't know the resistance of this one. That is going to be another problem for us. Yeah, the resistance, of course, we'll find it that way, then the way we found it for bulb. I think that is how we have to do it. Power is equal to P squared over R. Power is 72 watt. Sorry about the mishap, people. Power voltage is 12 into 12. Resistance is unknown. So R is equal to 144 over 72. That is 2 ohm. That is the resistance of the bulb, 2 ohm. So this is 2 ohm now. 2 ohm. This is also 2 ohm. There are 3 unknowns, people. I1, I2. Oh no, 4 unknowns. I1 and I2, ER. 4 unknowns are there. I need how many equations then? 3 equations, huh? let's name them. Name the circuit A, B, C, D. You have EF, GH. These are the terminals. Now we are going to apply Kirchhoff's law. So when you apply Kirchhoff's law, still what's the problem with this? My goodness. Both are closed. Same voltage. You need 4 equations, but I have only 2. Right. One thing, if we'll write everything we can write, first of all, we can say when you add I1 and I2, in fact, it is 8. I1 plus I2 is 8. If not, you can also write, if this is I1, instead of putting I2 there, no, we'll take it that way. Okay, I1 and I2, I1 plus I2 is 8. First equation. And if you apply Kirchhoff's law, come on, man. This resistor is known. R is unknown. He is also unknown. Wow. 2, 2, 1. Three or 4. No. Still there will be a problem. Anyone who found the values now? I'm trying to do this, people, but unable to get the answer. Sigma E. If I apply sigma E for this one, A B C D A for that circuit, if I apply the Kirchhoff's law, sigma E equals sigma IR. Yeah, okay. So sigma E, there's only one battery. We don't know the electromotive force. We'll take it as E, and the IR, sigma IR, the addition of IR multiplications, 8 ampere current is going through the internal resistance, so that is 8R, plus I1 current is going through 2.75 and 0.25. So I1, 2.75 plus 0.25, both are going both through both the resistors. I1 current is flowing. So I'm getting E equals 8R plus 3I1, another equation. And if I apply the equation now for A, F, E, D, A, that circuit in clockwise direction, again you can put sigma E equals sigma IR. Sigma E is still E, no change there. Sigma IR, 8R through the resistor, plus what? The current is I by 2, I2 by 2 into resistance 2. So E is equal to 8R plus I2. 8R plus I2. Then what can I say? This is the third equation. Then obviously I can, you see, when you equate second and third, you will be getting a relationship between I1 and I2. Second and third, when you equate them, because both are equal to E, you will be getting 8R plus 3I1 equal to 8R plus I2. So I2 is equal to 3I1. According to the equation, 3I1, 8R and 8R will get cancelled out. 3I1 is equal to I2. If 3I1 is equal to I2, we can say from the first equation, I can say I1 plus 3I1 is equal to 8. That means 4 I1 is equal to 8. I1 is equal to 2 ampere. I1 is equal to 2 ampere, and I2, that is equal to 6 ampere. I2 is equal to 6 ampere because I2 is 3 I1. So we have found I1 and I2. But unfortunately, even if I put it here, we will not be able to get a value. Now then, if I use the second equation, E plus 8R, so E equal to 8R plus 3 into I1. What is no second equation? Yeah, 8R plus I2. What is I2? 6. We can't write another equation in terms of E and R. That is the concern I have here. My goodness, what are we going to do? We are stuck. I don't see how to convert it, people. What's the time now? See, 3:30 already. My goodness, we are stuck, still stuck here. This is where we are. So I need another equation to solve for E and R. Power I2, what's the value of I2? I2 is just 3 square in 6 into 3 square into 2, just 18 watt. The resistance across them is 6, is it? 6. Same equation. Okay, we'll have to stop it there then. We'll have to stop it there, but without knowing simple R, we will not be able to do this question as well. And if I take it as 12 volt, does it help for us? If we take it as 12 volt, if you want to establish that 12 volt across these two, then there will be a current of 6 ampere here, 6 ampere here, which is impossible. Which is impossible. So if not, if you want 12 volt here, 12 volt here, then here also it will be 12 volt, then 4 ampere current is going here, for 2 ampere current, 2 ampere current. Still doesn't make sense. Okay, let's leave it like this. Next one, calculate the following when S1 is closed. When S1 is closed and S2 is open, right? S1 is closed, so this part doesn't work. Only this will work. Only when that works, R is 0.95, then 1.2 ohm on this side. Power delivered by the battery. The problem is, once again, we will not know the simple R. Without knowing simple R, we can't find the current. Okay, I'll leave this question and get back to this a little later. Okay, otherwise we'll be just circling around this question. Let's get back to this. I'm sorry, some problem is there. Right, next we'll go to the next question. Sorry. Right. We'll move on to the next one. We'll catch up soon. Define the electric current and potential difference between 2 points in a current carrying wire. So we know for A Roman 1, what is electric current? Electric current, its electric current is equal to electric charge flowing per unit time. No? So we'll write this electric charge over time. Can say what electric charge flowing per unit time. They are asking us to define electric charge flowing per unit time. And then potential difference. What is potential difference? Potential difference has an equation. We learned that in electric field, that is work done per unit charge. That is potential difference. Work done per unit charge. So we can define it as work done per unit charge. That is the definition for potential difference. Using the definition for I and V, show power dissipate between 2 points is okay. Yeah, okay. Then I think we have to use the same equation we used earlier. See, potential difference. I mean, we have already written it, so I can write it as V equals work done over charge. No? So V equals work done over charge. Work done is equal to QV. Just like the previous question, we divide by time. Dividing by time, when you divide by time, what will happen? You will be getting delta W over T, that is work done over time, equal to charge over time into V. Work done over time is power, charge over time is current, IV. Power is equal to IV. If the resistance between 2 points in the wire is R, show that R is equal to V square over, right? Fine. When we have already derived an equation for power, yeah, power is equal to VI, but we know according to Ohm's law, V equals, V equals IR, and the final equation current is missing, so we have to make current the subject. Current is equal to V over R. Therefore, power it is going to be equal to V into V over R, that is V squared over R. So we have to make R the subject. R is equal to V squared over power. I think for power they have used the symbol P, correct? Yep. Done, simple. So don't take these things for granted, the definitions and all. Sometimes they will ask you to do this in the first part. Consider the following two cases, and an electric appliance marked 2400 watt 110 volt design to be used in USA is plugged onto a 240 volt supply in Sri Lanka. An electric appliance marked 240 volt design to be used in Sri Lanka is plugged onto a 110 volt supply in USA. Explain, giving reasons. What would happen to each case? What will happen? Let's discuss quickly. Sorry, wait. Okay, hold on. So under B1, let's see what's going to happen. B1, they have given the power and the volt. So we can use that equation. Power is equal to, they had asked us to derive an equation, people. What is that? R is equal to V squared over power. So resistance equal to Roman 1, V squared is 110 into 110 over power is what? Power is 2400. So resistance is 11 into 11 over 24 ohm. 11 into 11 over 24 ohm, that is the resistance of that. Now we are plugging it to 240 volt, this is the resistance. And now yeah, that's done. And when we know power is equal to VI. So when I say rated power is equal to rated voltage into rated current. When you say rated current, the maximum possible current through that. So rated power is 240 and rated voltage is 110. And let's say what is the rated current? Rated current is going to be how much? 2400 divided by 110, that is 240 over 11. So when I divide 240 by 11, I'll be getting 2 to 20, that is 1. In 90, there is like 8. Okay, I'll say 21.9 ampere. Okay, right, 21.9 ampere. That is a rated current through that equipment. When a voltage of 240 volt is provided, what will happen? Provided, what will happen? We can apply V equals IR, voltage. We are applying 240. Current through the circuit we don't know. Resistance, here we have found it, that is 11 into 11 over 24. So we are getting a current of 240 into 24 over 11 by 11 into 11. Okay, when you multiply 24 and 24, what do you get? 576, if I can remember right. Yeah, 576. 24 into 24 is 576 into 0 over 11 into 11 is 121. So when you divide them, what is the current we are getting? The current is more than the rated current. Current we are going to get is more than the rated current. And how much is that? 576, 5760 divided by 121, 47.6 ampere. But the rated current is just 21.9 ampere. So what will happen? So equipment will get damaged. Similarly, if you take Roman 2, what's going to happen, Vivo? Roman 2, of course, now R equals V squared over P. And let's quickly finish this off, just like the previous one. V squared is 240 into 240, the rated voltage, and the rated power is 2400. And this is easy, 0, 0, 0 cancels out. 24 also cancels, it's 24 ohm. Yeah, gone, 24, 24 gone, it's 24. So we know R now. And when you put equal Vi, Azan will just continue, right? Now this is what's going to happen. The first one, I found the rated current, maximum allowable current through the equipment in both. What did I do? Very first, what did I do? I found the resistors. I found the resistors of each equipment based on the given power and voltage. So we found it, and then based on the voltage supplied to that equipment, we found the new current through the equipment. So the first equipment, the new current was 47.6. but the rated current is just 21.9. So we are sending a current which is much larger than its rated current. So if you plug that, as soon as you plug it, the instrument will burn. It was too much current. Here the current going through the equipment is 4.58 ampere, but the rated current is 10 ampere. That means we can for the proper functioning, optimum functioning of the equipment, we need 10 ampere current. So the equipment is not going to get damaged, but I don't think it will work properly, because we need at least 10 ampere current for a proper function of that instrument. But we get only 4.58, so we might not be able to use it in optimum level, but it's not going to get damaged. So I think that's why they're expecting from us, giving reasons. We are supposed to explain what's going to happen. So if you plug if your rated voltage is 110, if you plug a high voltage, it's going to get damaged. If your rated voltage is 240 and if you plug a low voltage, it's not going to get damaged, but it's not going to work properly as well. Okay, done. Then let's move on to the next part. Okay, so this is another question. This question is entirely based on power. So let's see what this is all about. Next part. Circuit breakers are automatic switches that protect against dangerously large total current by opening to stop the current when it exceeds a specific safe value. Once safe conditions are re-established, the switches can be reset. Given that household power circuits use a number of power points connected in parallel, consider the following situation. So you might have seen at your home, you have this box. You have a box like this, a box like this. Now modern days you have boxes like this, and inside you will have first of all you will have the main switch. You'll have the main switch like this. So if you turn it off, it will the entire house will not have the current. Okay, entire house will not have the current. And then what do you have after that? After that you have the trip switch. After that you have the trip switch. That is when there is a problem, if the trip switch falls down, the current in the circuit current in the entire household will stop. Okay, sometimes when there's a problem in your electric equipment in kitchen, sometimes blenders and all these iron boxes, if they have a problem issue, then this there's a excess current going to flow, then this trip switch will fall down. Main switch, it is not automatic. Trip switch is automatic. Okay, this is main switch. This is the trip switch. Trip switch, it is automatic. So once it has fallen down, when it has turned off, the current won't. There will be no current in the house. Then you can put it up. You can put it up only if there is no leak anywhere in the house. If there is a leak in the house, if you turn it on, again it will fall down automatically. You might have come across those situations. And after, next to that, you have the other components. These small other switches. Not they will look similar to this. These other small switches are called circuit breakers. What about the circuit breakers? What is their significance? They will be connected to each different part of the house. For example, if there is a problem in the kitchen, sometimes this will turn off. The circuit breaker which is connected to kitchen will turn off. In the other places of the house, you will have current. Both will happen. Sometimes the entire current will stop. Sometimes only in a certain area current will go. That is governed by this, what do you call that, circuit breakers. Now for example, if you have a repair to do in your kitchen, you can turn off the circuit breaker which is connected to the kitchen and you can do the repair work. But it's usually recommended to turn off the main switch and do the repair work. But still, sometimes electricians, they do that. So this is the idea behind that delivery box you have in your house. In a kitchen, a 1440 watt toaster, a 960 watt electric kettle and a 480 watt microwave oven are plugged into different power points in the same circuit and connected through an 11 ampere circuit breaker to the 200 volt household power supply. I think they had mentioned something clearly. What is it? Given that household power circuits use a number of power points connected in parallel. Okay, so plugged into different power points in the same circuit and connected through 11 ampere circuit breaker to the 200 volt household power supply. Draw a circuit diagram showing how appliances are connected. Let's start number 1. So the current supply, people, that is 200 volt. Okay, 200 volt supply. I'll just put it as 200 volt like this. It is a AC supply in Notion, so with 200 volt supply. And what is this? This is the circuit breaker. Circuit breaker is like a fuse circuit breaker, and it will have what, 11 ampere. What is the meaning of this 11 ampere? Meaning of the 11 ampere is, if a current more than 11 ampere flows through it, it will burn and it will stop allowing current through it. That's the idea behind it. And then you have a toaster, you can think of it as a resistor, and then you have a what, electric kettle. Don't forget there will be switches. So let's say the switch is on here, I don't know, switch is on, toaster, then you have electric kettle, and then you have microwave on. If they are working, that means the switch is on. Okay, so you have to think of the appliances as resistors. You have to think of the appliances as resistors like this. Okay. Good. Now what is this power? This is 1440 watt. 1440 watt. And what about this one? This is 960 watt. And this one is 480 watt. Right? Okay. So that is the circuit. Okay, parallel. They must be parallel, and they must be connected to this circuit breaker and the supply. Roman 2. Calculate the current drawn by each appliance. So first of all, let's consider the toaster. What is the equation I should be using, people, to find the current? Let's see. Send me the answers, people. What is the equation I should be using to find the current? Anyone? Good. P equals VI. That's all. P equals VI for toaster. P equal VI. P 1440 equal to voltage is 240, because everything is connected in parallel. So all of them will be experiencing a voltage of 240 volt. That is not going to change. All of them are going to experience that voltage, 240 volt. And yeah, this is also 240 volt, because they are connected in parallel, and they are not talking about any internal resistance. So we can say all of them experiencing same. And the currents, now 3 different currents are going to flow, I1, I2 and I3, and the total current coming in, it is I. So this I can't exceed 11 ampere. If it exceeds 11 ampere, this will burn. Right, let's start then. Current through this P equal into I1, and what is the answer, people? I1, I think it's equal to 144 over 24, 6 ampere. No, 6 ampere. And then that is for toaster. And then we'll apply it for the next equipment. What is the next equipment? Kettle, electric kettle. So for electric kettle, if you apply the equation, again power equals to VI. Power of electric kettle is 960 equal to voltage. Voltage, how much is the voltage, people? Which is the voltage? 240. Current is I2. It sends a problem here. I2 is equal to I2 is equal to how much? I2 is equal to 960 or 4 ampere, no? 4 ampere. Then what is the next one? Next one is the microwave oven. Microwave oven. For that, when you apply P equal VI, power is 480 watt, current is I3 into voltage is 240 and current is I3. So what do you think is going to happen here? Now I3 is equal to 2 ampere. Total current is 12 ampere. So if you turn on everything at once, it is not, the circuit breaker is going to turn off. Okay, so we have found the current, done. Find the resistance of each appliance. How do you find the resistance of each appliance? For that, I think we derived an equation a little while ago, Roman 3. That is also simple. You can use this equation. R equals V squared over P, power. V squared over power. So first of all, for toast, if you apply that equation, toaster R1, that is equal to 240 into 240 divided by power of toast is 1440. I think that will be 240 over 1440 is 6, 240 over 6 is 240 over 6 is 40 ohm, correct? It's 40 ohm, okay, 40, no? Yeah, 40 ohm. And then next one is for kettle, electric. I'll just put kettle for the time being. Kettle, for kettle, when you find the resistance R2, that is 240 into 240 divided by the power is 960. 240 over 960 is 4, 244 is 60 ohm. Correct me if I'm wrong, 60 ohm. And finally, for microwave oven, for microwave oven, when you apply the equation, the new resistance R3 is equal to 240 into 240 over the resistance is, the resistance power is 480, so that is 120 ohm. 120 ohm, alright, 120 ohm, yes. These are the resistors, done. Roman 4. Calculate the equivalent resistance of the three appliances when all three are turned on at the same time. What is it? 1 over R, it's going to be equal to 1 over R1. That is how you have to do it, 3 resistors, plus 1 over R2 plus 1 over R3. So 1 over R is the equivalent resistance, 1 over R1, 1 over 40 plus 1 over 60 plus 1 over 120. Then 1 over R, it's equal to, you can take 1 over 120 as the common denominator, 3 plus 2 plus 1, is it? Yeah, it is 6 over 120, therefore it is 1 over 20. So R, I'll say R equivalent is going to be equal to 20 ohm. When all three appliances are turned on at the same time, will the circuit breaker open? Circuit breaker open means, what's the meaning? Circuit breaker open means, either here, it will stop the current. Here, circuit breakers are automatic switches that protect against dangerously large total current by opening to stop the current. So it's like switch off. Opening means switch off. So what will be the total current? Now you can redraw that circuit if you want. You can redraw that circuit 240 volt, and you can put just R equivalent. R equivalent, and don't forget the circuit breaker or the fuse. It will be 11 ampere fuse we are using, so 11 ampere circuit breaker, and R equivalent is equal to how much? 20 ohm. So if you try to find the current now, sigma E equals sigma IR. They have not given an internal resistance for the circuit breaker. 240 equal to sigma IR is I into 20, so current is 12 ohm. Greater than 11 ohm. 12, not ohm, 12 ampere, greater than 11 ampere. So circuit breaker will open. Circuit breaker will open. Will be opened. Right, that's it. It's a very simple question. So anyone who found these answers, people? Hurry up. It's pretty straightforward. When you look at these things, it might look a bit intimidating, but quite manageable. Okay, quite manageable. You just have to use the power equation, power and then Ohm's law equation. That's it. Done. Even with O-level knowledge, you can do this. Even O-level knowledge, you can do this. Then moving on. 3 electrical appliances ABC rated 6 watt, 6 volt, 0.5 ampere and 20, what is this? 3 of them. So wait, I'll underline them separately. A, this is A, and these are the values for A. B, these are the 2 values for B, careful. C, these are the 2 values for C. So for A and C, they have given the power and the voltage, but for B they have given the power and the current. So let's be mindful about that. Okay. Are to be connected in parallel with a cell of EMF 10 volt and an internal resistance of 0.5 ohm with additional electrical components. What is the total current that should be supplied by the cell for proper operation of the above appliances connected in a circuit as stated above? Show that a single cell of the given type is unable to supply the necessary current to satisfactorily operate all the appliances stated above. Good. First of all, total current. Now let's apply this equation. Now d1. So I'm going to use this equation. Now we know power is equal to Vi. Power is equal to Vi, and now rated power is equal to rated voltage multiplied by rated current. So we need to maintain rated voltage and rated current for proper functioning of the instrument. Then if I make rated current the subject, that is equal to rated power over rated voltage. Now they have already given us the rated current for B. We don't have to calculate it separately, but for A and B they haven't. So for A, if I apply the equation rated current, for A the rated current is going to be the rated current, will take it as IA. I'll put IA, okay, wait, IAR, right? Rated current for A, that is equal to rated power for A is 6 watt over 6 is 1 ampere. So we need 1 ampere current through A. Then for C, if you apply the rated current for C, let's term it as ICR, that is equal to power 27 and the voltage is 9. So 2709, that is 3 ampere. 3 ampere. So total current required is how much? Total current, and I'm going to directly write rated current for B. IB rated current for B. That is already given in the question to us, and what is the value, people? You can see that is 0.5 ampere, correct? 0.5 ampere, it is already provided to us. So total current required, how much? So total current required is equal to 1 plus 3 plus 0.5, and that is how much? 1 plus 3 plus 0.5, that is equal to 4.5 ampere. Is it 4.5 ampere? 4.5 ampere. Right, good. Then Roman 2. Now if you go to that circuit, now let's connect the circuit and all the appliances. Appliance A, then you have appliance B, appliance B, A, B, and finally C. So when they say appliances, we can consider them as normal resistors. Right, for proper functioning, that's what they're saying. Show that a single cell of a given type is unable to supply necessary current to satisfactorily operate all the appliances. To satisfactorily operate all the appliances, what should I say? Current through each circuit, current through each appliance, current through each appliance must be rated current. Rated current. What is the total current that should be supplied by the cell for proper operation of our plants? Right, fine. Connected in parallel with the cell and with additional electrical components. Okay, then it is 10 volt. This one is 10 volt and it has an internal resistance of how much? 0.5 ohm. So we will tell me the currents through each circuit. What about the currents? The current through A has to be 1 ampere. Current through B has to be 3 ampere, sorry, not 3 ampere, 0.5 ampere, and current through C has to be how much? That also should be, no, that is 3 ampere. Okay, fine. That means the total current which is coming out of the battery should be 4.5 ampere. Now, how do we decide whether this is good or not? We have to find out the voltage across the battery, V. We have to find out the voltage across the battery. So, for battery, if you apply V equals E minus IR, we can apply that's the equation, people. So, V is V, we don't know. EMF is 10 minus current is 4.5 into resistance. How much is resistance? 0.5. So, V is equal to 10 minus 2.25, final answer 7.75 volt. 7.75 volt. Is this good enough? Is it good enough here? 7.75 volt, is it good enough? Tell me. Show that a single cell of the given type is unable to supply. So, my question, this is the amount of voltage it can create, amount of net voltage it can give out to the circuit when current of 4.5 ampere is coming out of it. Now, listen, this needs a voltage of how much? Just 6 volt. This needs a voltage of 6 volt. That's okay. We can put a resistor here. Out of 7.75, this can take 6 and the remaining 1.75 can be taken by another resistor. B needs a voltage of how much? 4 volt. So, for B it will take 4 volt and the remaining 3.75 can be taken by another resistor. But for C there is a problem. For C people, the rated voltage is 9 volt. This is okay. Now, this is 6 volt, this is 4 volt, we can measure 4 volt. Now, for B, if you apply rated power is equal to rated voltage into rated current, rated power is 2, rated voltage we don't know, and for current is 0.5. So, rated voltage for B, it's going to be 2 divided 0.5, 4 volts. 4 volt is enough. 4 volt is enough. So, you can put another resistor here. You can put another resistor here and allow it to take the remaining voltage. Okay, I will draw that. But C is a problem. 7.75. But C requires a voltage of 9 volt across it. So, this battery is not sufficient. Understood? That's all. Just follow the instructions in each questions. They are assisting you with this. First question, they are asking us to find the total current. So, when you put the total current here, then you can find out how much maximum voltage this can create across it, and you can compare that with each of them. So, for A, okay. With this I can say with this so 7.75 I can say A and B are okay. A and B can work satisfactorily, but not C. They are saying show that a single given type is unable to supply the necessary current to satisfy operation of all the appliances. That's the issue. A and B can work, but C cannot work. That means it's not all the appliances in the people. Good. So, I hope you guys understood it, how to adjust the power. The previous question was a flop, but I think this one was somewhat okay. Good. Now, let's see another one. Right, there's another question. I hope this one would work properly. Let's see. What's the time now? 4:10 now. Okay. Right, question number 3. Does the third question say? Electromotive force of an electric source is defined as the work done by source on a unit charge. Using the definition of electromotive force, find the unit of EMF. An expression for the power delivered by an electric source in terms of, okay, fine, this one we have already done it, but anyways, let's just for formalities finish it off. So unit of EMF, it's like this. It's going to be voltage now. EMF, now it's like this. Now EMF, unit of EMF or dimensions of EMF, according to the definition, it is work done over charge, work done per unit charge, or energy supplied per unit charge. Energy supplied per unit charge. So that is also similar to voltage. So unit of EMF should be, even though it is electromotive force, it is volt, V. An expression for the power, find an expression for the power. I think I explained it earlier. Work done, or it's like EMF E is equal to power or work done over charge. And what do we do? Work done over charge, and we wrote it as delta W over Q, and delta W over Q, and then we will make delta W the subject again, which is E Q. Either side we divided by time, delta W over time, work done over time, equal to EMF into electric charge over time. Work done over time is power, and EMF is E, Q over T is current, so EI. Once again, power is equal to EI. This is the power generated by an electric source, EI. An electric source having EMF E and internal resistance simple R is connected to an external resistance of capital R. Right, let's draw the circuit, simple circuit, done. So this is ER, this is capital R, ER, capital R. And we know there's going to be a current flowing through the circuit. Now same current will flow through, will be generated from the battery, and the same current will flow through that external resistor capital R as well. Obtain an expression for the energy dissipated in the circuit in terms of T, in terms of E, R, capital R and simple T. So we can say what? We have derived an equation for power. So we know power generated by battery, no, wait, we'll write it this way. Okay, power generated by battery is equal to power dissipated in the resistors. Power dissipated in the resistors. So total power dissipated in the resistors. Now power generated by that, so that is so total power generated or dissipated, total power dissipated will be given by what? Will be given by EI. We have already derived the equation, EI, but the problem is I is not there in the answer. I is not there in the answer. For the circuit, for this particular circuit, let's apply sigma E equals sigma IR. Sigma E is just E, but sigma IR is I times simple R plus capital R, because current I is flowing through both simple R plus capital R. Therefore, I that is equal to E over simple R plus capital R. If I substitute it here, E multiplied by E over capital R plus simple R. Therefore, the answer is E squared over capital R plus simple R. Well, that is for power dissipated, but the question is about energy dissipated, right? So energy dissipated is in fact what? Energy dissipated. Energy dissipated is in fact power into time. Power is E squared over capital R plus simple R multiplied by time is T, simple T. Therefore, final answer E squared T over capital R plus simple R. This is the final equation. Very simple. even though it looks complicated. If you follow the basic steps, getting the final answer is not difficult. So the total power dissipated will be the total power generated by the battery. Done. Again, a question about power. And now let's, I really hope this one will work, because the previous question was a flop about the circuit. I hope this one will be helpful. This one will work. Okay. People, right, wait, I think I might have to consider one at a time. So let's first focus on this question, the question here. First, let's focus on part 1. Okay, part 1. The figure shows the electric bulb L1 rated 12 volt 6 watt. Okay, an electric fan having an internal resistance 8 ohm connected in series. It's connected to a cell having internal resistance and EMF 24 volt. There is an internal resistance, we don't know what that is. So I'll put it as simple R here. Another electric bulb labeled as L2 and rated 20 volt and 10 watt is connected in parallel across F and L1. So they have given, they are just describing the diagram. They're just describing the diagram. So what are we supposed to do? Since we are doing the first question, let's make the adjustments in the given diagram for our first question. So it's easier for us. Yeah. This one has an internal resistance, simple one. If the bulb L2 glows with normal brightness when key S1 is closed, so we have to close S1. We have to close S1, right? We have to close S1, right? When I close S1, according to this question, should I close S2? What are the other questions? Current through bulb L2, the internal resistance of the cell, the power supplied by the cell to the circuit. Okay, so this is open, this is open, and they are saying it works with normal brightness. Bulb L2 glows with normal brightness. So what can we say then? So rated current flows through bulb L2. Now in the earlier question they had not mentioned that a rated current is flowing or something like that. They had not mentioned that. So let's we couldn't take it that way. Now a rated current is flowing. First of all, let's find out the rated current of that bulb. So first Roman 1 for the bulb L2. Let's apply rated power is equal to rated voltage multiplied by rated current. So the rated power of that bulb L2 is 10 watt, 10. Rated voltage is 20, and the rated current, we don't know how much is the rated current. Then rated current is going to be half, isn't it? Half ampere. Current is going to be 10 over 20, that is half ampere. Okay, we have found it. That's what they are asking, right? Okay. The internal resistance of the cell, number 2. Now there's going to be a current flowing, half ampere current flowing. Half ampere current is flowing, and no current through this path, people. Why is that? This path is disconnected. Okay, no current. So we can focus only on this. For circuit, we can apply sigma E equals sigma IR. Sigma E is 24 equals sigma IR, current is 0.5, and there's a total resistance of okay, interesting. There's total resistance of how much? You can do it this way. Wait, now if it is functioning properly across this, there must be a potential drop of how much, people? 20 volt. No? There must be a potential drop of 20 volt. So you can write this way, sigma IR, one is 0.5 into R, okay, plus here it is going to be 20. Why did I put 20? Why did I put 20? The reason for putting 20 there is it needs 20 volt for the proper functioning. So out of this 24, 20 is taken by this. That's what I put IR for this one, 20. So So 4 is equal to 0.5 R, and we are unusually getting a large value for simple R. Simple R is going to be equal to how much? 4 over half. So that is 8 ohm, which is pretty unusual for an internal resistance, people. 8 ohm. Yeah, I didn't make a mistake here, right? Current glows with normal brightness. We need to know that current, otherwise we can't do this question, and there's R is unknown. Okay, what to do then? Right, let's continue. Third one, the power supplied by the cell to the circuit. Power supplied by the cell to the circuit. Power supplied by cell. What is the equation? We just derived it a little while ago. Power supplied by the cell, that is equal to electromotive force multiplied by I. That's all. Electromotive force is 24. Current is half. Therefore, it is supplying a 12 watt power. So it supplied 12 watt. Out of that, 10 watt was taken by the bulb L2, and the remaining 2 watt was dissipated inside this resistor. Understood? That is what's happening here. Yeah. So those are the 3 answers, but this internal resistance value is quite unusual. 8 ohm. That's a very high value, but we will have to continue with that. Done. We'll move on to the next part. Roman 2 now. We have to start it from the scratch. People, now we know the internal resistance, that is 8 ohm from the previous question. Now I will cover Roman 1 and Roman 3. Okay, Roman 1 and Roman 3. Wait a minute. Where is that? Roman 1 and Roman 3. I will cover that. Right, Roman 1 and Roman 3. Let's focus only on Roman 2. But before I focus on Roman 2, I have to mention the fact that its internal resistance is 8 ohm. Right. Roman 2. What does Roman 2 say? Find the following as at the instant the key S2 is closed while S1 is kept open. Now S2 is closed. So the diagram changes slightly now, right? This is the scenario we have to focus on now. S2 is closed. So if there's a current coming out of the battery, that current, the entire current, I'll take it as I2. The entire current is going to flow through the outer path. There's going to be no current through L2. So L2 will not work. L2 will not work because that circuit is disconnected. The resistance of electric bulb L1. Okay. The current through the electric fan, the power supplied by the cell to the circuit. How do I find it? Okay, the resistance of the bulb means, people, that can be found easily. How is that? Roman 2 part 1 for bulb L1, right? L1, we can use this equation. We know power is equal to V squared over R. So R is equal to V squared over power. So resistance is equal to V squared. It is 12, 12 into 12 over power 6. What is the answer? 144 over 6. If not, you don't have to make it too complicated. 12 and 6, you can simplify them. Here 1, here 2. So 12 into 2, obviously 24 ohm. 24 ohm. That is the resistance of bulb L1. Okay. The current through electric fan. The second one, current through electric fan. Now, how many resistors are working? 1, 2, 3 resistors are working. This has a resistance. Now we found the resistance. It is 24 ohm. 24 ohm. The current through this is I2. They are asking for I2. Then for circuit, you can apply Kirchhoff's law. For the circuit, if you apply Kirchhoff's law, sigma E equals sigma IR. How much is that going to be? Sigma E, only one battery, that is 24. When you put the current, it's I2. There is only one path open. So through all the appliances, same current is going to flow. Total resistance, you have to be careful. 8, that is the internal resistance of the battery. 8, that is for the fan, plus 24, that is for the bulb. Therefore, 24 is equal to I2 multiplied by 40, correct? So, what is I2? I2 is equal to 24 divided by 40, and that is 0.6 ampere. 0.6 ampere. Then third one, the power supplied by the cell to the circuit. Again, same equation. Power supplied by cell. Remember, power supplied by cell is given by electromotive force multiplied by current coming out of the battery. Electromotive force of the battery is 24. The current coming out of the battery is 0.6 ampere. 0.6. So 24 multiplied by 0.6 is 14.4 watt. 24 into 6 is 144, but it is 0.6, so we have to make it 14.4. That's it. Okay, so you will have to draw a separate diagram and do the question. We can forget about the middle part. You have to focus on only on the path through which the current is flowing. Done. That is part 2. So we missed the earlier question, but this question is I think hopefully covering it up. And then Roman 3. Right, Roman 3, Roman 3, yeah. And the circuit is important. We need the circuit. The circuit is ready. Roman 3 is visible to us, and that means we need to get rid of 1 and 2. Okay, wait, what's the question? So for second one, can't we apply P equal to VI for bulb? Second one, current through the electric. Which one? For second one, can't we apply P equal VI for bulb? P equal VI for bulb. Yeah, you can. Are we getting the same answer? 2 ampere. No. No. Oh, wait. We are not getting the same answer, no? No, Amna. No, you can't. Here they have not told that the bulb is glowing with the brightness, no? They have not mentioned that the bulb is glowing with normal brightness. So you can't apply that. That's why it's wrong. They are asking to find the resistance of the bulb, no? That's why. So what is the current through the bulb? The rated current through the bulb is 2 ampere, no? But the current flowing was how much? How much was the current? Current was how much was the current? 0.6 ampere. So that's okay. This bulb is not going to glow with normal brightness. This bulb is not going to glow with normal brightness. Yeah, because when you have resistance like this with 8 ohm, it can't happen. So if you apply V equal P equal power equal VI for the bulb and find the current through the fan, that is wrong, because you can use that rated current only if the bulb is functioning with normal brightness. No, that's wrong. That's what I'm saying, Amna. You can't do that because they have not mentioned the fact that the bulb is glowing with normal brightness. They have not told anywhere, right? But for the previous question, they have mentioned. They have mentioned that the bulb is glowing with normal brightness, but here they have not told that. Wait. Okay, that's the problem. I found the current and applied it to find R, but I got 24 ohm for that. That's the problem. And you can't do that. Careful, huh? You can use the rated current as the current through the bulb only if they have clearly mentioned the fact that bulb is glowing with normal brightness. If not, you can't use that. Right. So it's a good learning partner, learning curve. Right. Learn something new. Now we move on to question number 3. When only S2 is closed. When only S2 is closed. So I have to cover all these parts and then mark the other information, which is the internal resistance, simple R. How much was the simple R, people? 8 ohm. Is it 8 ohm? No? 8 ohm. When only when only S2 is closed, when only S2 is closed, what's happening? Yeah, when only S2 is closed, the electric fan accelerates and reaches steady velocity after a short time, and then L1 glows as rated. L1 glows as rated. See, they are saying L1 glows as rated. What is the meaning of that one? That means yeah, L1 is glowing as rated. That means it has the current required. Okay. At this stage, find the current through the electric bulb. Explain why the current presently in the circuit is less than the current at the instance closing S2. Earlier question was about that, right? Earlier question also you closed S2, wasn't it? Number 2. Let's read this again. Read this again. When only S2 is closed, okay, the electric fan accelerates and reach a steady velocity after a short time, and then L1 glows as rated. What do you think is happening there? Maybe maybe its resistance is changing. Okay. Explain why the current presently in the circuit is less than the current at the instant of closing the key 2. Calculate the induced back EMF by the fan when it's working at a steady state. Now, there's something called back EMF, people. When you have a motor, in that motor, there will be a, now we haven't learned, we learned that in magnetic field. Okay, we learned that in magnetic field. When there is a motor, you have a magnet, you have a conductor rotating around the magnet. So inside the motor there will be an electromotive force induced, but in the opposite direction. That's what we call a back EMF. So wherever you have now a fan means it is connected to a motor, right? So in a motor will get the current from this and it will rotate. As a result of its rotation, inside the motor there will be a electromotive force created in the opposite direction. That's what you call back EMF. So when only S2 is closed, the electric fan accelerates and reach a steady velocity after a short time, and then L1 glows as rated. If L1 is glowing as rated, what's happening? We have the rated current flowing through that. 2 ampere is flowing. Interesting. Oh yeah, okay. That means the current is reducing here. Oh, current is reducing? No. Yeah. Okay, something is happening. Let's see. Again, we have to close S2. Now for third question, we have to close S2 because they have clearly mentioned that S2 is closed. So if S2 is closed, we can forget about S1. No, because shall I erase it? Okay, I'll erase this part. I'll erase this part because it's, oh no, we'll leave it. If not, no, we will be drawing a new diagram. So we don't want these things in that new diagram, seriously. We don't want these things in the new diagram. We'll get rid of them because S2 is closed. S1 is still open. Only S2 is closed. They have clearly mentioned that. So there's no point of drawing the middle part really. We'll get rid of the entire middle part because no current will flow through that. So it's useless. Okay. Right. Yeah. At this stage, find the current through the electric bulb. Now, Roman 3. We have to find the rated current. Rated current, Roman 3. Let's go for that equation. Power rated, it's equal to voltage, rated voltage into rated current. This is important. And then L1 glows as rated. So rated power is 6. Current, sorry, voltage 12. And what's the current? Rated I. Okay. Then now rated current is how much? Rated current is going to be wait a minute, 6 over 12, we are getting half ampere, na? Half ampere. Amna, what was the earlier current? The current before in the previous question? Was it 0.6 or 0.4? 0.6. Then there's a problem, na? If it is 0.6, then the bulb should get damaged, na, people. So that's a weird thing now. According to the previous question, we got a current which is 0.6. Oh my goodness, now this is a problem. We are getting problems. There's no other way of doing it, right? 0.5 ampere. Let's see. 1. Okay, 1. And then second one, explain why the current presently in the circuit is less than the current at the instance of closing the key to. The reason for that is this. Can you remember we were talking about something called a back EMF? We were talking about something called a back EMF. So that back EMF is the reason. Back EMF means when a motor rotates, when the motor in the fan rotates, it will generate an EMF in the direction opposite to the direction of existing battery, opposite to the direction of main power source battery. In the direction opposite to the direction of EMF of main battery. Okay, now I hope you all have observed this. When you turn on a vehicle, at the beginning the bulb will go brighter when you turn on the switch, when you put on the key. I don't know if you have seen this, raise your hands. Especially in lorries and all, you'll be able to notice this. When you turn on the key, before you start the engine, you will see the bulbs glowing brighter, and then suddenly when the engine starts and when the motor starts rotating, the brightness of the bulb will reduce. I don't know whether you have noticed or not. That is exactly what's happening. So when if the engine is working, you see something rotating inside, no? When you see something rotating inside. So when it rotates, the motor is working. When the motor works, it creates a back EMF. We call it back EMF. So we mark it like this, actually, the opposite direction, because original EMF is in clockwise direction. Back EMF will be in the opposite direction, like this way. Sorry, this way. E will put it back EMF. There will be a back EMF in the motor. We will be learning about that in magnetic field, but there's nothing much. Even though we learned that in magnetic field, you will again come back to Kirchhoff's law and apply. Only thing is, think of it as a new battery in the opposite direction. That's all. That is what you call back EMF. So when suddenly there's a EMF in the opposite direction, total net EMF will reduce. No, net EMF will reduce. What we're saying, when the motor in the fan rotates, it will generate an EMF in the direction opposite to the direction of EMF of main battery. So net EMF reduces. Net EMF reduces. Hence current reduces. But in this question, there's a problem. The initial current is greater than the rated current. So I think there's a problem with the numbers they have given, but there's no other way of handling this question. Let's continue. Third one, calculate the induced back EMF by the fan when it's working at steady state. So now for the circuit, we have to apply Kirchhoff's law. Now for the circuit, when you apply Kirchhoff's law, sigma E equals sigma IR. Tell me, what is sigma E now? What is sigma E? Okay, sigma E is going to be 24, that is from the main battery, minus back EMF, equal to current. Current is, now we have found the current, 0.5 ampere is the current. 0.5 ampere is the current flowing through the circuit now. Same current will be flowing through here also, 0.5 ampere. So IR, what is IR? Current is 0.5 now, and that current is flowing through 8 ohm. This is also 8 ohm. And what is the resistance of the bulb, people? We found it. What was the resistance of the bulb? Power is equal to V square R. What was it? 6 over V square over 24, no? 24. Correct me if I'm wrong. 24, no? 24. Correct? 24, yes, 24. 24, yes, thank you. So if it is 24, then this is 24 minus back EMF equal to half into 40, half into 40, that is 20. So what is back EMF? Back EMF is equal to 24 minus 20, and that is 4 volt. Right. So these answers are looking pretty reasonable, but the only issue is the first initial current we calculated with the information they have given was greater than this value. So that is a problem, but I think they might have gone ahead with the same answer in the scheme. They must adjust one of these resistors. Maybe they should increase this to maybe a 10 ohm or something, then only this question is correct. But anyways, with the data they have given, those are the answers we can get. Okay, good question again. So first one didn't work out our way, but this one is somewhat okay. Done. So that's the end of the third question, is it? That's the end of the third question. And there's another one. Yeah. This one is a big one. So let's see how far we can go in that. This is, yeah, okay. Last part, D part of third question. A student decided to use cells each having EMF 6 volt of internal resistance 4 ohm. What is the minimum number of cells required for this purpose, and illustrate with a diagram how they must be connected. What is this, Vivo? A student decided to use cells each having EMF 6 volt and internal resistance 4 ohm. What is the minimum number of cells required for this purpose, and illustrate with a diagram how they must be connected. Now what is the already existing cell? Now the already existing cell we have is 24 volt. That is its EMF. Wait, I'll draw the other stuff. There was a fan. There was a fan, and then there was something else. What was that? The other one? Motor? No, bulb. No. Oh, okay. So fan and the bulb were there, L1, and the EMF of this battery was 24 volt, and internal resistance is 8 ohm. Remember, internal resistance is 8 ohm. So I need to achieve this using these batteries. What is our plan? So a quick revision: when you have two batteries like this, and when you put them in series, both are E and R, E comma R, because they have identical cells. They are trying to use ER, ER, yeah. Then that is equivalent to what? When you put them in series, it will be equivalent to a battery of 2E and 2R. Both are series, so both should be added. But when you put them in parallel, what will happen? When we put them in parallel, what happens is you have E here, R, and here also E comma R, and that is equivalent to what? EMF will remain as E, no change, but resistance will become R by 2. Resistance will become R by 2. So to achieve 6 volt, EMF, achieve 24 volt EMF, I definitely need 4 6 volt batteries in the series. Let me draw that. I will definitely need 4 6 volt batteries in series. There's no other option, no people, no other option. But when you put them in series like that, there is a problem. Can someone tell me what's the problem? What's the problem now? So this is 6 volt, 8 ohm. Sorry, 6 volt 4 ohm. 6 volt 4 ohm, 6 volt 4 ohm. Here also 6 volt 4 ohm. Here also 6 volt 4 ohm. Now I have 24 volt, no problem. But the resistance is how many? Resistance is 16 ohm internal resistance. But I want the internal resistance to be how much? I want it to be 8. So I have 16. Then to make that 8, I will need another line of exactly the same setup. Do you agree with me or not? See if you can understand this one. This one, correct? So you put another line, 6 volt, sorry 6 volt, 6 volt, 6 volt, 6 volt, and here 4 ohm, 4 ohm, and another 4 ohm and 4 ohm. Right, fine. This is it. This should be the correct answer. And then the remaining part should be connected to the fan and whatever it is. Right, you have the fan here, and you have the bulb L1 and F. Okay, people. So what I'm trying to tell you here is, now this part you have to analyze it carefully. The part I have marked here, 4 batteries in series. I have changed the signs now. My goodness, I have changed the signs. Sorry, everyone, wait. I have to change the sign. Sorry. Right, okay, wait, let's change it. Come on. 6 volt, the positive side must be here. So altogether we need a minimum of how many batteries? 8 batteries. 8. Because with 4 with just 4 we can achieve the EMF we need, but we can't achieve the internal resistance we need. So to get that internal resistance we need, we will need to change it. Now these 4 together will be, if you take them as one battery, 24 volt, here also 24 volt, but the internal resistance is different. What is the internal resistance here? 16 ohm, here 16 ohm. Then those two together now can be taken as a single battery. When you put two batteries with equal EMF, the EMF, resultant EMF doesn't change, but when you put two resistors in parallel, resistance becomes half. Okay, so this should be the setup. They are asking, illustrate with a diagram. So this should be the final answer, because a student decided to use cells each having EMF 6 volt and internal resistance 4 ohm. This is how the setup should look like. There is no other way. So you have to analyze this way. Good question once again. And I have received a, let's see, save it. I hope you guys understood this. Really cool one. Yeah, that's a problem. Okay, good. Now let's move on to the next part. Last question, but I think this is a little lengthy, so let's quickly see what it's all about. I think we have to finish the first theory part. No, they have given a theory part and they are asking some questions. So let's quickly finish it up. Sorry. Right. What do you mean by ohmic law? Sorry, ohmic conductor. No? Ohmic conductor. So A Roman 1, if you answer. A Roman 1, what do you mean by ohmic conductor? A conductor which obeys Ohm's law, which obeys Ohm's law. If not, in other words, or we can say a conductor through which current is directly proportional to the electric potential difference. Current in which electric current is directly proportional to the electric potential difference across the conductor. Done. Draw IV characteristic curve for ohmic conductor. That is simple. We have done it before. Just V equal IR. So you have IV characteristic means you can put I here, V here. Doesn't matter who is where. It is definitely going to be a line which goes through the origin of the axis. Yes. And Roman 2. What is Roman 2? Write down separately what happens to the electrical conductors, insulators and semiconductors as the current flows through them as the temperature increases. Now for conductors, what happens? Conductors, when temperature increases, resistance increases. So current will increase at a decreasing rate. Current will current will increase at a decreasing rate. Current will increase at a decreasing rate. Current will increase at a decreasing rate with voltage. That is for conductors. And then for insulators, what will happen to people? For insulators, when temperature increases, what will happen to insulators, people? Insulators means stuff like rubber, plastic, resistance, I think it should reduces slightly. That's all. Resistance reduces slightly. No significant change in current, we'll put it that way, because the insulators, no significant change in current, because insulators do not have a ability to release electrons. And then semiconductors are a little special. Semiconductors, what will happen? Semiconductors, when temperature increases, more free electrons and holes will be released. So what will happen to the resistance? Released. So resistance reduces. If resistance reduces, what will happen to current? Current increases at increasing rate. Current increases at increasing rate with voltage. Okay, that is Roman 2. So what I'm trying to tell you is this. When you plot the graph, IR graph for a conductor, the graph is going to look like this. For a conductor, IR graph, IV graph, the graph is going to be like this. This is for conductor, remember, like something like a filament bulb for a conductor, not an ohmic conductor, normal conductor. Ohmic conductor, it will be straight line, but for a semiconductor, resistance reduces. So current will increase in increasing rate. Current and voltage will increase this way. This is the I versus V, because they are asking IV characteristic. IV characteristic means we put current on y-axis and voltage on x-axis. That is the answer for Roman 2. Write down the equation of Kirchhoff's second law and identify all the symbols in it. Roman 3, second equation, it is sigma E equals sigma IR. Sigma E is net EMF, net EMF. Sigma IR is sum of multiplications between current and resistance. Okay, Roman 4. Write down an equation for electric power in terms of I and R. Oh, that's simple. They are just asking us to write down, not obtain. So P is equal to I squared R. That's all. So look, the first part of the question, they are expecting you to know certain theory parts. So don't take the theory parts for granted. You can score few free marks here. Out of 15, maybe 3 or 4 marks, you can score freely if you know the theory. That's enough. Done. That's so that's going to be a good start for you for the question. Then you will have the confidence to face the other part. Right. In day-to-day life, fans are used to quench the sweat. The ceiling fans. Give me a second. The ceiling fans as well as table fans are most commonly used in homes and offices. The following figure shows the internal circuit of a table fan. So it looks a little complicated. Let's see. So it looks a little complicated, but I hope we'll be able to manage. So there's a capacitor. See, interesting. Capacitor will not allow current to flow through it. Capacitor will not allow current to flow through it. Current will flow through only in the outer circuit. And remember, these switches, if these switches are off, then current can't flow, no? Because the circuit is disconnected. So when they say one is open, we'll consider, right? We'll tell me if the questions are readable or too small. I'll read the question.
Yes,
so
sir.
You get that right. Thank you. So yeah, we'll take it this way because I will need the diagram as well as I will need the diagram and I have to mark the information provided on the diagram. Yeah. So yep, this is enough, I believe. Yep, it is enough, right? Let's prepare the screen so that we can use the other parts of the screen to write our answers. Good. The speed of the rotating blades can be controlled by button switches. Yes, you have fans, everyone knows this. There are two coils in the motor named as the driving coil and the starting coil. Driving coil, starting coil. The capacitor is connected in series with the driving coil. Yeah. The starting coil is connected in parallel to both capacitor and the driving coil. Okay. So when there is no current through the starting coil, capacitor will give out the current, so the driving coil will work. I don't know. Right. Let's see. Right. Consider the capacitor is labeled as 400 volt 2.2 microfarad. No. Yeah. They have labeled it and they have written it again. So we'll write it once again here. What is it? It's labeled as 2.2 microfarad. That is its capacitance. Hope you all can remember we did the electric field. But we did in electric field 400 volt. Consider the instance of the button 1 is switched on. So now button 1 is switched on. Therefore, I have to take button 1 in. That means this part is complete. This circuit is complete now. Circuit is complete. Switch on. Button 1 is on. Right? This circuit is complete. That means current will flow. How? Current can flow starting from 240 ohm, 40 volt. We'll take that current as I1. It can flow like this. It can flow through this. Remember, it will not flow through these two. We'll just cut these two parts because they are useless. Switch off, and then the current will keep flowing this way. I1, then current will flow like this. I1, current will continue to flow like this. I1, I1, and I1. No current will flow through the capacitor because capacitor will be fully charged. No? Steady state. We have to consider this for steady state. Yeah. Okay. So this is how the current will flow. Consider the instance button 1. Name the path of the flowing current through the closed circuit using the English letters marked in the figure. Oh, interesting. So you can say A, B, A, B, E, correct? F, G, H, K, and is there a letter here? L. All right, interesting. That's it. Find the value of the current through the circuit in this instance. So Roman 2, B Roman 2, how do you find it? B Roman 2 for circuit, let's apply Kirchhoff's law. They have earlier also they asked Kirchhoff's law, sigma E equals sigma IR. I am not going to worry about the current going through the capacitor, capacitor through capacitor. We can assume that current doesn't flow. It should be fully charged. No? Sigma E, there's only one battery, that is 240. What is the current I2? And that current I2 is flowing through how many resistors? 120, 120, 240. 120 plus 120 plus 240. Is it going to flow through anything else? No. It can't flow through this 210 because the capacitor will not allow the current to flow through it. Remember. So, yeah, that's it. Then I'm getting 240 equal to I2 into 480. So I2 is equal to 240 over 480. Final answer, half ampere, 0.5 ampere. Okay, 0.5 ampere. Done. Determine the potential difference across the starting coil. What is the potential difference across the starting coil? For Roman 3, for starting coil, we can apply V equal IR. For starting coil, we can apply V equal IR. So V is equal to I, current 0.5, and the resistance of that is 240 volt ohm. So the answer is 120 volt. Okay, 120 volt. So we are done with this, done with this, done with this. Find the power consumption of the starting coil. Again, easy. For starting coil, okay, right here. For starting coil, let's use the power equation. What is the power equation? I think this also they had asked in the previous part. Power is equal to I squared R. I squared R. So I squared is 0.5 squared, that is quarter, 0.25 into R. Its resistance is how much, people? Starting coil 240. So 1 over 4 into 240, that is 60 watt. 60 watt. Determine the potential difference across the capacitor using the above results. What will be the potential difference across the capacitor, people? Now, starting coil will be like this. Capacitor is like this. And remember, even though there is another driving coil or whatever, there's going to be no current through this circuit. So this is useless. This 210 ohm, there will be no potential drop across the couple down. No, across this potential difference is 0. So if I have a potential difference of how much, 120 volt across this one, I will have the same potential difference across the capacitor too. Determine the potential difference across the capacitor and the above results, 120 volt. That's all. That is the answer. Why? Because capacitor and who is that? Starting coil are parallel to each other. They are parallel to each other. Okay. Yeah. Determine the okay, that's done. Determine the energy stored in the capacitor. So they have given an answer. Don't know whether that's the correct answer. I'll get rid of that. What is the equation for energy stored in the capacitor? Someone? Krishnika, Amna? Anyone? 6-1. What is the equation? Energy stored in capacitor. What is the equation? According to this context, we can go with half CV squared. Correct? We shouldn't go for any other equation because we don't still know the charge across that. No? But we know the potential across that, and they have given us the capacitance in the question, 2.2 microfarad. They have given that already. So we'll use that equation, half CV squared, that is going to be half into, you have to be careful, C, 2.2 microfarad. So let's put 2.2 into 10 to the power minus 6. Normally it will be in picofarad. Okay, fine. Now microfarad is also okay. Into voltage square. What is the voltage across the capacitor? 120 square. 120 squared. So it is 1.1 into 120 into 120 into 10 to the power minus 6. What is going to be the final answer? 144, 14,400. So 144 into 1.1 is 1,440 plus 144 plus 14.4, that is 158.4. When you multiply all these numbers, 158.4 into 10 to the power minus 4. People, I borrowed these two zeros and put it with this, so it becomes 10 to the power minus 4. 12 into 20 is 144. 144 into 1.1 is 158.4. How did I find 158.4? 144 into 11 will be 144 plus 14.4. Yeah, so this is the answer. Final answer, you can take it as 1.584 into 10 to the power minus 2 joules. No, people, this is not the answer they had got. Anyone got this answer? Hurry up. Anyone who got this answer? I'm getting 1.584 into 10 to the power minus 2 joules, not the answer they had written here. They had got 1.584, that's all. Did I make any mistake? I hope not. 1.584, so I'll stick to this. Calculate the power of the motor to the nearest whole number. Power of the motor. Power of the motor, didn't we find that? Nearest whole number. Power of the motor. We know the energy. How do we find the power? Power of the motor. So we know the energy stored in the capacitor. Calculate the power of the motor to the nearest whole number. They are asking for the power of the motor, part of the motor. The entire thing is part of the motor. So starting coil has a power dissipation 600 watt. My question is, how are we going to find power for capacitor? Driving coil is also there. By what number should we multiply that? We will divide it. A little confused right now. For time, is the problem. Power of the motor to the nearest whole number. Power of the motor to the nearest whole number. Power dissipation in the starter coil we have found, no? Power consumption of the starter coil we found it, 660 watt. Now they are asking power of the motor, and the energy stored in the capacitor is also there. So capacitor has some energy stored in it. What if we turn off the capacitor then? No, what if we turn off this thing? 450 ohm. We'll discuss the last part. Is a bit confusing, no? Last part, people, no current will flow through this, but there's an energy stored. Let's see. Last part, I'm not very sure. So let's discuss that later. Okay. Anyways, so these are the answers. Analysis about this circuit. Not a bad one. Good. And let's see what's they're going to do next. Part 2. Part C, I think. Part C. Part simple B. Yeah. Okay. Part A done. Part simple B. Yeah, continuously asking to determine the power of the motor. Okay. Now part B, if you take part B, you might have to reduce the size of this. Okay. Again, they are asking you to determine the power of the motor. I don't know what they expect us to do there. in the next question also. Let's see. Okay, they are going to put now switch to, let me cover part A, and let's focus on part B now. Right. Now consider the instance of the button 2 switched on. So when you put the second button on, current won't flow through B and D, but path C will be completed like this. So we can get rid of the other two paths. No current flow this, no current through this. Name the path following the current through the closed circuit used in English letters. Okay, now just like the previous example, now current is going to take a different path. The current, I will take it as I2. Now current will flow through this path, then current will flow through this path, and then it will take this path to flow through this I2, and the entire current will go through H again, I2, and then again I2, and once again here I2. Done. So that is going to be A, B, C, F, G, H, K, L, A. Find the starting current through the circuit in this instance. So again, Roman 2, we can apply sigma E equals sigma IR. Sigma is once again 240. This time current I2, but it doesn't, it is flowing through how many circuits now, how many resistors now? It's flowing through 120 ohm, 240 ohm, that's all. It doesn't flow through this. So it should be 120 plus 240. So I2 people, that is equal to 240 divided by 360. That is 2 by 3 ampere. If not, I2 is going to be equal to 0.67 ampere. Determine the power of the starting coil. Okay, then Roman 3. Starting coil. For starting coil, what's the power, people? Power is equal to I squared R. So this time to find the power, I will use this value, 2 by 3 twice, 2 by 3 into 2 by 3 multiplied by 240. What's the final answer? Getting 80, 320, okay, wait, 3 and 240, we can simplify them and put an 80. Four into 80, that is 320 over 3. 320 over 3, and that is equal to 106.67 watt. Determine the power of the motor. Now how do we do that? We will determine the power of the motor. Once again, across this one there will be a energy stored across the capacitor. Wondering how to prove it now. How do you connect these two? This is the power of the starter coil. We need to divide the energy stored in the capacitor by some time. So how do we find the time? That's what I'm wondering. Any suggestions? Initial current we know. Okay, let's try to do this, people. Initial current is 0.67. Hope I find it, people. There is an equation, but it's not there in our syllabus. There's an equation to find the time taken for the capacitor to get charged or something like that. But that equation is not there in our syllabus. There's this diagram for the capacitor. No? When the capacitor is getting charged, current through the capacitor reduces like this. There's an so for that I initial current I naught, there's an equation. I is equal to I naught e to the power minus some t over RC or some equation like that. It's not in our syllabus. So using this we find the, I have taught the London A levels, there we use the syllabus, they have the calculator and everything, it's not that hard. But the problem is we don't have that in here. So when you have a graph like this, how to find the current? There's no way you can find the time here. This is the time taken for the capacitor to fully charge. So it's a curve now, people. If it's a straight line, at least you can find it. Fine, never mind. So let's leave it. Let's continue to the next part. B part, switch 3, okay. After switching on each and every button switches. Write down what happens when power of the motor when switching on each and every button switches. When can you say about, what can you say about the consumed power of the table fan when the button switched 1, 2 and 3 are switched on? Determine the number of energy units when the above table fan working 2 hours per day for 3 days at a speed rate relevant to button 3. So the problem is we need to figure out a way to find the power of the motor. Right, so when the third switch is on, you can do the same math again. What will happen when the third switch is on, people? Right, when third switch is on, we are supposed to find out, that is part D. No, part C. We'll do it separately. Part C, we'll find the current quickly. So when third switch is on, this path will be closed. And these two paths will not work. These two paths will not work. So there will be a new current now, I3 flowing. This is answer for part C. When switch switch 3 is closed. Now, current, if I mark I3, new current I3, and that current will flow from, it will flow this way, it will flow this way, it will flow here. It will not go down because it can't go down. This path is disconnected. And then an I3 comes like this, I3 comes like this, I3 goes like this, and I3 finally comes back to the battery. So now if you put sigma E equals sigma IR, sigma E is 240, sigma IR is I3 into 240, that's all. These two will not work. These two, there will be no current through this. No current to this, no current to this, no current to this as well, because capacitor is fully charged. Then the current is just 1 ampere. I3 is equal to 1 ampere. Now for starter motor, starter coil or whatever, starting coil, we can use power equals I squared R. The same thing we are repeating. Power is unknown. Power into I squared is 1 squared into R. R is 240. So now the power is 240 watt. So looks like third one is the higher speed one, no? Because the more power is consumed there. First one it was 60, 240, sorry, 60 or 120, 240 if I can remember right. Yeah. So that is how the switches are working. We put 1 slow, 2 moderately fast, 3 fastest. But then the problem is, how do you find the power of the motor as a whole? There's the capacitor, so I feel like there's a link between capacitor and that, but how do we find it, people? Right, okay, let's save this. This is for part C. Done. So for everything we need to know that power. Determine the power of the motor and current through the circuit when the button switch 3 is switched on. Write down what happens to the power of the motor when switching on each and every button switches. What can you say about the consumed power of table fan when the button switched 1, 2 and 3 are switched on? When all 3 are switched on, what will happen? What will happen when you switch on all 3, people? When you switch on all 3, what will happen when all 3 are switched on? Shall we? That's what they're saying. No? What can you say about the consumed power of the table fan when the button switched 1, 2 switches 1, 2, 3 and 1, 2 and 3 are switched on? All 3 are switched on. Then what will happen? Tell you. people? They are, wait, now this 60 volt, they have given, someone has marked in the question, that is wrong. That is not always true. No? That's not always true. So let's just get rid of that. When you switch on all three, what will happen? Let's prepare the area. Wait a minute. When all three switches are switched on, what is that question number? D, right? Simple D. Okay. D. Current will flow through only switch 3. Yeah, very good. That's correct. Fantastic. Yes, that is correct. What is it? Now, D part, when all three switches are on, what will happen? Right, let me quickly draw that and finish it off. This is on, this is on, this is also on. So what happens is a certain parts are going to be short circuited. So everything is switched on now. This path is closed. This path is also closed. This path is also closed. Now what will happen to the current? Current will flow like this. I4, I4, I4. Now current can avoid these two resistors. Current can avoid these two resistors and it can go here. So these two resistors are in fact what? Short circuited. That's why you should not put them all together. So it's like switch 3 is on, I4. There will be current I4. So what will be the value of I4? I4 will be equal to 1 ampere because it's similar to I3 is on. Because, sorry, not similar to I3 is on, similar to only switch 3 on. Only switch 3 on. So you have to be a little careful now. You don't want to turn on everything together because there's no point in that. Turning on everything together and turning on just 3, it's identical. Okay, right. So that is also done. That's okay. So, but the problematic part is that what is the power dissipation in the fan, the total fan? Right, fine. I'll check that and try to figure out a way to connect the energy stored in the capacitor and see if I can find a connection for power, because energy stored in the capacitor. So power, to find power, we need to find a time to divide it, but what time are we going to divide it? That's the concern I have. Fine, then I'll just check it and let you know.